So let's actually talk about what transformers do. So first off, the reason why AC is kind of superior in terms of transmitting electricity from one point to another is because of transformers. And transformers don't work in DC circuits or don't work for DC currents. It only works for AC or alternating currents. Okay. So what's so different about alternating currents and direct currents? Well, there is a magnetic effect, if you can remember. So I don't know if you remember, but let me give you a review of that. So if there is a wire and there is a current through that wire, okay, so let me draw it like this. There is a current through that wire, then a magnetic field is created around that wire. Okay, so in this direction there is a magnetic field. This works like a magnet, right? At every point it works like a magnet. But those magnetic fields are fixed if the current is fixed, right? So if there is a current, there is a magnetic field, and if the current is a constant current, the magnetic field is also constant. But what happens if that current keeps changing? So in this wire, at first the current is with a high value, so there is a huge magnetic field, but at some point later the current is low. So like, let me draw it with a smaller arrow. Then the magnetic field is kind of also small. So I'm just drawing this as a just notation. Don't take this for later. Don't take this literally. So the magnetic field also shrinks, and you can imagine if there was no current through that wire, there would be no magnetic field. And if the current starts moving in the opposite direction, well, the magnetic field also starts moving in the opposite direction, and this continues. So the magnetic field in AC is not constant like DC, right? So the magnetic field is continuously changing. And if you can remember that changing magnetic field actually induces electric current. So in DC, what happens that you have electricity, and that gets converted into magnetism. Okay, let me just write it, magnetism. But in AC, what happens is there's electricity, and that gets converted into magnetism, and it also converts back into electricity. So there's kind of a reverse way, and there's a kind of back and forth between these two types of energy, right? And this is what a transformer uses. Okay, so a transformer is a very simple object. You have a wire here and you have another wire here. Okay, so if there is an AC current here, so I'm drawing it 2 arrows, there will be changing magnetic fields. Okay, changing magnetic fields creates electric currents on the other winding as well. So there is also an AC current, and this is used everywhere. For example, wireless charging uses this exact technology. Okay, so this is basically a transformer, one on your charger and one on your phone, right? But in transformers, this whole thing is actually just one device. Either way, what's important is the fact that there is a back and forth between electric energy and magnetic energy. And this energy, since we know that energy is conserved, we can actually use this technique. So we know that power is equals to V times I. So maybe if the current is higher here, so like V times I am drawing the I large, so the current is very high here. So you can imagine where there is a plant, we are generating high amount of current, right? That plant will distribute this current in national grids or something like that, a huge area, right? So that's a huge amount of current, although the voltage is quite okay. All right, so the power is something like this. There's relatively low voltage but a very high amount of current. But there is a problem with that, because high amount of current produces high amount of heat when moving through wires. So you can imagine that this is like Kaptai, and you are generating a high amount of current, and you are trying to send that electricity to, let's say, Dhaka. Okay, so you have to cross an insane amount of distance, right? And if you have a high amount of current, we know that even if this has a small amount of resistance, it's still a long way, so that becomes a very large resistance. And not to mention, the power is actually proportional to the square of current. So this is already a huge value, and if you square them, that's even larger value. So this power is just lost because this resistance there in the wire is just perfectly useless. We don't need that at all, but we can get rid of that either, because every wire has some amount of resistance, and if that's this long, definitely there is going to be some resistance. Okay, and so what happens that this energy is lost as heat. So this heats up, and a lot of energy is actually lost in the process, so if you use this high amount of current. Okay, and this is where actually DC fails. We cannot use DC for this exact reason, that there is a high amount of current and we can just do nothing about that. But transformer in AC circuits provides a way that we can use different coils. Okay, so maybe we can use high amount of coils here and low amount of coil here, or vice versa. Okay, so depending on the number of coils, we can actually convert this power is conserved, or energy is conserved, so we can actually convert between this voltage and current. So we can actually increase the voltage. Okay, so the power is the same as before. Okay, so I'm trying to draw the power in the same size, but what happens is that the voltage gets large and the current becomes very small, right? So this is how the back and forth between electricity and magnetism works. Okay, so this electrical energy becomes magnetic energy, okay, in the flux, then it gets converted back to electrical energy. But we change up things here, or we change the number of coils, and that makes the voltage very high but the current very low. Okay, so that's the trick transformers use, and that is why AC is successful, right? Because if the current is very low, the resistance here is also the power loss here is also very low, because, well, the current is low, and so it's fine that if there's a low power loss, there will be always some power loss. We can't avoid that. Okay, but it's much less than before. So that's exactly why we use AC. And so the voltages we see on transformers are much higher than our house, the voltages in our houses. So our houses uses 220 volt, and this is 50 hertz AC. Okay, so I have talked about that earlier. So each second the electrons are moving back and forth 50 times, and the voltage is 220 volt. You will see these written on like your chargers and stuff, that it should be plugged into a 220 volt charger. And this is what the British system also uses, 220 volt, and almost most of the part of the world except for US uses 120 volt. So be careful, and that's also 60 hertz. So the systems don't actually match. Okay, so be careful when buying a phone or something from US. Okay, because you have to ask for the UK version of the charger, because that's not if you use a 110 charger in Bangladesh, it's going to blow up, because it's not made for 100, it's made for 110 volts, not for 220 volt. So you have to ask for the 220 volt charger. Okay, 220 volt 50 hertz charger. So that's the thing about AC. You have to be careful what voltage and frequency you are using, but that's something you also have to worry about in DC circuits as well. Even not the frequency, but at least the voltage you are working with, right? So this is very similar to DC, but with the added benefit of transformer. Okay, so we won't actually go into details of transformers, but definitely we are going to discuss heuristically here. We actually want to analyze alternating currents. Okay, so now at this point we understand AC is much better for transmission. Okay, and high power devices uses AC, but that doesn't mean we can work with it, because the whole point of circuit analysis is to predict how much voltage there is. Okay, so you don't want anyone to die, so you should know how much voltage or current is going on there before sending your worker there, right? So that's the whole point of circuit analysis. We want to theoretically calculate the voltage and currents before actually sending a human. So if you were thinking, well, that's just going to be a 30 volt 30 volt line, that's fine. You can touch it with little shock, right? But if that's 30,000 volt, that's not good for anyone, right? So if anyone touches that, it's just going to blow up right away. Okay, so for example, sometimes you see crows just blowing up on transmission lines. Okay, so you have to be careful, and we do circuit analysis to avoid human casualties like that. Okay, so that's why we need to learn how to calculate stuff and calculate stuffs. And we have seen how we calculate DC circuits, so we are fine with that. But the problem is now we have a completely new different system, right? So we have a voltage source. So this is how we draw. So we have a voltage source, and we actually write how much voltage it's using. So let's say this is 10 volt, but this is a sinusoidal voltage, right? So let me write it like this, maybe sine 60, maybe something like that, or 60 plus 30 degrees or something like that. This can be many things, and we'll discuss that later as well. But I just wanted to mention that since the voltages were oscillating, you need a sine or cosine function for these types of stuff, right? So this is a cosine function we are going to use here, and you can have resistances. Okay, you can have other stuffs we have already seen. So you can also have current sources that also has the same type of frequency. Okay, so it has to have, for now we are going to restrict it to the same number just for simplicity. This 6 needs to remain same. So maybe we are going to use like 10, okay, let's use a different number like 5 sine 60 minus 40 degree, maybe, I don't know. Okay, so this can be many things, right? And you can have resistances and etc, etc. And there is also another interesting thing about alternating circuits, that you can have capacitors and inductors just like normal DC circuits. So it turns out if you use a inductor or a capacitor, or anything like that, okay, I just drew it in this weird way because I don't know where to put it, but just like normal DC circuits, you can use inductors and capacitors. But the fact is that when we learned about capacitors and inductors, it was a different set of circuits. It was transient circuits, right? But in AC circuit, they work just like resistors. So we'll see that these capacitors, inductors, and resistors kind of behave in the same way. Okay, so you can think of them as like resistors in some sense. Okay, so there's a new name for them. We actually call Z. We actually denote everything by Z and call them impedance. Okay, impedance. So this is something we are going to work with, and impedance kind of generalizes resistors, capacitors, and inductors, and everything. Okay, so that's our new goal, how we are going to calculate things. Now, you might be afraid, okay, how do we do this or something like that? Do we need to invent something, learn something new things? Well, here is a genius idea. Let's use everything we have learned before, except instead of using real numbers, let's use complex number. Okay, so that's a huge benefit. Okay, using complex number to use the same techniques we have learned for DC will work here if you use complex number. So this is one of the most important part of engineering, that using one technique of one area into another technique, another area. So using complex numbers, we will see that this problem turns into just like a DC problem, but except for these values in DC, where every number is real number, those becomes a complex number. Okay, so let's do that. Let's do a complex number review. Okay, so before we go into the details of how to solve a AC circuit, we are going to do a complex number review because a lot of you haven't taken complex number course yet. So we are going to do that next. Thank you.